So I'm happy now to introduce the closing keynote, which will be presented by Akio Kasuga. You already seen Akio sometimes in this symposium. Akio is the current president of FIB. He is a well-known bridge designer, well-known for being a very innovative bridge designer. He has designed several very innovative bridges in Japan, and he is also he chairs a large group of engineers and scientists which are working for the research and development department of a very important company called Sumitomo in Japan. So, please, Akio.
Radio. Thank you for your very, very kind introduction to me. So, hello, everybody. Last part of the presentation, and please be patient a little bit. So today's topic is towards the sound conceptual design. So thank you. Already said, I'm minor participants among this more than 100 people, because I'm from a construction company, but the Japanese construction company is a little bit unique. We do the detailed design in especially the highway bridges. So we have a design section and also R&D center inside of the company. I have experience more than 200 bridges design, and I have experience of the 4 bridge construction site. Okay. So this is contents today's presentation. Everything is based on my more than 40 years experience in a construction company. So last time in Spain, this time in Swiss. So everybody has set their own definition of the conceptual design. So today I have factors and tools of conceptual design and constraints and lesson from the existing structures and R&D to the conceptual design to realize the conceptual design. And finally, I have to talk about structure sustainability. The first one is factors, design built and influenced by the great designers and experience. So this is a chart of the design. The right-hand side is through life management. And everybody says at the beginning of the project, after the investigation site and everything, the conceptual design starts. And the conceptual design starts before the feasibility, and also after we getting constraints and performance requirements, the conceptual design starts. And inside the contents of the conceptual design, the Fugo already mentioned in the first day in his presentation. So everybody knows Eugene Freycinet. He's very famous, and he's the same as me. He belonged in the construction company and also design. So this is very famous. I like this bridge, Precast. And at that time, mainly the bridge was iron. But after this construction, the cost of the bridge is almost half and 1/3 of the iron bridge. So his name is spreaded all over the world after this construction. And Troha, I love him very much too. And he has a very, very innovative way of thinking. And also this is very famous shell structures. And after the design, he confirmed to the real size, the model test. So at that time, there were no sophisticated software. Every designers confirmed the strengths by the test. And Finsterwalder, he's a father of the free cantilevering method. At that time, there was the processing steel, strand steel, and also in order to make sure the free cantilevering method, the Finsterwalder in Viaduct invented the Viaduct bar. So this technology introduced to Japan in 1950s. So the before the rapid economic growth after the World War II, this kind of technology helps a lot. And Morandi, he's also the very, very innovative designer and also builder, and especially right-hand side, lowering of the arch. In Japan, we still use this technology in the many construction sites of the arch bridges because it is economic compared with the free cantilevering method. So why were they so creative? I think they were not only designer, but also builders. So from problem solution to problem finding is very important. Problem solution is we call needs. Needs, everybody think about. But problem findings, it's a niche. Niches, nobody think about that. So every time I tell my young engineer to make the innovative structure from the niche. So we have to think about problem findings. This is a word, the Matiba. Unfortunately, I had no chance to meet him, but this was I heard from the Professor Stucchi of the Brazil. Design should take into account how to build it. I fully agree with it, his words. And also I had a very, very big influence from many great designers. My favorite designer is Jan Mueller. I met a couple of times. And in 1993, when I was in the Odawara Blue Way Bridge construction site, he visited us. And this photo shows that this is just during the competition of the Mio Viaduct. He explained me the 600-meter arch construction. And this is whiteboard that it is a little bit hard to see, but he explained me to how to build it, what is the concept of the 600-meter arch. And I followed his concept in especially cross-section of the cable stayed bridge, Logroño Bridge, and the CD Canal in the United States, and Israel in France. So optimization of cross-section, I love cross-section very much because every way of thinking is concentrated into the cross-section. So especially the cable supported structure, the clear flow of forces is very important, and it's a key of cable supported structure, I think. The cable support points should be very, very close to the wave to transfer the force from the cable to the girder immediately. So the transverse stiffness in a very wide cross section is the key of the design, conceptual design of the cross section. After the John Mueller's work, and I copied his cross section, and also I analyzed his way. But sometimes I modified his conceptual design cross section. This is a 33 meter on single plane of the Euskalduna Bridge in the highway. Finally, the owner chose this one, but the stiffness stiffened by rib is not enough. So the 3 diaphragm were needed in this construction. So it's not easy to the construction site. And also I use the same technique, but the finally reinforcement of the cross beam and also the longitudinal small beam is needed in this is a 24 meter wide section. And another example is how to construct the corrugated steel wave bridge by using the partial precast technique. It used very, very well because after the detailed design, the construction starts. If the design was not efficient, the project's manager complained us. So it is very severe design in the construction company. This is an example in a highway over the river. And in order to reduce the weight of the whole superstructure, finally we apply this cross-section, much lighter than the conventional box girder. And this is also work in construction over the levee of the river. The core segment is free cantilevering and fastly to the abutment. And after that, the side part of the girder is constructed by the home travelers. It works well too. And the experience, everybody knows the Rome was not built in a day. I agree. In 1990, I was in the United States in the UT at Austin, and Olivier was the same, and we are the office mate. And I don't know, he knows this contest. This contest is the part of the fractional mechanics by the Professor Yura. I didn't take his course, but the contest, span contest was open of all of the civil engineering department. I had 10 years experience at that time, and also there are many very smart master students and some PhD students. So I applied this contest, and I announced my friends, if I lose, I quit the engineer, because I have confidence. So this is very easy. Span length is only 30 centimeter, and also every year the loading point is different. In this case, the loading point is wider than the support, and also the position is the center of the span. But loading height is variable. It depends on the design. Everybody knows the optimum structure is truss. The shortest way to the loading point to the bearing point. It is very clear. The point is the angle of the truss. Everybody knows about 45 degrees, 50 degrees. So I chose this area. Oh, so the material is balsa. We pay $9. So the balsa and epoxy resin given by the office. So this is the result. And the criteria of the contest is the maximum load divided by the model weight. this is very interesting. Number one and number two is different from another student. So the finally, sorry, I won. I got $90 and go to the sushi restaurant. So this is experience. Bruce, now he's a professor of the United States, and he had 5 years experience in the company. So me, I have 10 years, but rest of the students has just a student. And also Bruce model is the same as me. So it's very close, but finally I won. I'm very happy. And I realized the structure, the design needs experience a lot. And second is tools. You know that this is sketch of Fresnay. He think about the inside of the structure. And also he draws some very simple calculation, which the Paul likes this sketch. And me, I use a 5mm graph paper. It's very convenient because I need the scale. I need a precise scale in a sketch level because I think about construction way. So this is the example to develop the suspension structure. I draw many sketch. So the Toha, you know, he thought every day, and finally he reached the solution of the shell and confirmed by using a real size test. But now, young engineers, you have very sophisticated tools, but we have not overcome, we have not reached over the Toha's level. Why? Please think about that. So you have a very sophisticated tools. You can try in a very short time, but Toha reach the directly the solution through the long time way of thinking. So we have to think about the difference. So sound conceptual design, everybody talk about that. I agree. Only the pen and paper, it's enough. No sophisticated software, no very thick specification are not needed. Only the paper and the pen. You agree, okay? So think about, again, why the difference come from in this present time. Okay, next one, constraints. I love constraints very much because if you have many constraints, we can challenge a lot. So sometimes the carved bridge, it's very difficult, lightweight or cost, construction time, especially in the construction company. So we have many Constraints, especially the alignment. This is a Japanese expressway, and also alignment is S shape. In this bridge, we don't use the ordinary box girder because of the transport condition of the steel. So finally, designer decided to use cable stay bridge, but this is very clever. So the tower point is inflection point. So you can imagine the lateral force, this side and this side is equal. So finally, the tower shape is very slender. I love this structure. And this is our work. And the bridge located on the national park. So we could not use temporary support and piers. So finally, we have to build single span structure by using a suspension structure. This is the photo of during construction. The suspension force is anchored into the ground. But after the completion, this anchor forces transfer to the girder. So about 12,000 kilonewton force transfer to the girder. Finally, the force go to the deck, upper deck, and also the cord. Mainly the upper cord, because the stiffness of the upper cord is much stiffer than the lower. So finally, the structure is simple supported structure. So key of sound conceptual design is strict constraints and performance requirements stimulate designers challenge mind of sound conceptual design. I fully agree. So we need a lesson for the conceptual design, the communication with designers through the structures. Miguel Astis from Spain, he gave us a paper, it is a Japanese magazine, that his title was Structural Engineers Can Communicate with Designers Through the Structures. I understand, he said. The structures are the common language, he said, among designers. Maybe most of the people can agree these words. And I'll show you some examples. This is Euskalduna Bridge in Bilbao. I visited this bridge. Curved bridge, but the truss is only one side, the anti-symmetrical structure. It's very difficult. And I walked through the pedestrian area. The roof is very, very huge. And at that time, I had a tour guide, Japanese tour guide, and I asked him, why do you think? He said, Bilbao is a very rainy city. So at that moment, I understand, I am convinced. But Miguel sent me the drawings. So I found that the roof is not just a roof. This is structural members, because you can see the beam is the stiffer for the lateral direction in order to suppress the lateral deformation of the truss. I understand, and also the roof is works as a structure part of this. So this is very, very smart solution, but I have not confirmed the Miguel, this is right or not. But just I read the designer's conceptual design through the structures itself. And another, his work, Logroño Bridge, is very unique. You can see the very, very shallow arch and also the curved pedestrian bridge. And this is very important, that this cable is anchored into the abutment. We can see the diameter of the cable is much larger than the rest of the cables. So this is the solution. The lateral force by the cable is not only the hanging, the pedestrian parts, but also in order to stable the very shallow arch. The force is compensate of the horizontal arch. So this is also, I love this bridge, and I understand. Just, I never been there, but I just see the photos of the structures. Okay, Fuga's work is very, very clever. So the widening bridge is very, very difficult. And we discussing now, but we will launch the new model code 2020 with, I hopefully, the next year. But at the same time, we introduce the new construction at the same time, the existing structures, the same manner of the design. The intervention is after the evaluation of the old structure, we go to the conceptual design, exactly the same as the new construction. So this bridge built in 1986, the 150-meter cantilevering method, and they widen bridge. How? This is a solution, and the new construction weight go through the strut, and finally the load carried by the new web. So how do they do that? So this is the solution. This photo is much clearer. The connection between the new construction and old structure is only the center. This is anchor. So I understand that every road, this is the cantilever parts from the strut to the center of the web. So it is very, very good solution. Congratulations, Fugo. Oh, this is very, very clever. So we can read the designer's conceptual design philosophy through the structure. Please see the very, very clever structure. Not just visit the site or just read the paper, and you can imagine why the designer do the design like this solution. And please read the philosophy. So this is very special conceptual design from the R&D. We, as a construction company, we have the many requirements from the site, cost and the construction time. And sometimes my company is specialized in the concrete bridges. So we have to compete with the steel structures sometimes. In this case, this is a highway. I designed this bridge. And the constraints of the project is concurrent engineering. Concurrent engineering is the project started, and during the detailed design, we tried to the new technologies with R&D. Mainly this bridge is we confirmed the real size test. Cost reduction, of course, and this bridge located into the local town, so we have to reduce the construction time to reduce the segments number. So the left-hand side is a basic design by consultant, and the right-hand side is our detailed design. So we remove the deck, and also we widen extending the segmental length from 1.9 to 2.6. So finally, we reduce the number of segment 9000 to the 1300. It's 72%. And this is a very big advantage for us. The girder weight is a basic design in 900 tons. In the detailed design, 330 tons that we can reduce up to 37%. So we saved €2 million. So the owner said, okay, we did the real size test at the construction site. So this is the scheme of the construction. We use a precast panel and cast in situ. This is a test to confirm, because the U shape has the very, very small stiffness of the torsion. At the site, we cast the concrete in each area. So we assume that the worst case, which means that the big torsion occurs, But finally, it is okay. We are very happy. This is the photos during construction. And the last R&D example is the butterfly web. The constraints, the project, the cost reduction, and also the construction buildability, lightweight, because the substructure is another construction company done by the couple of years ago. After that, our seismic code renewed. So the design by the consultant company was conventional box girder type. If we apply the conventional type, we have to strengthen the substructure according to the new seismic code. So the client highway company asked us to reduce the structure weight, but they don't want to use corrugated steel web. So this is a sketch. We took about 13 years before this sketch after we analyzed and R&D ourselves. And finally, we spent 13 years to realize the butterfly concept. So firstly, we think about the butterfly shape panel as a steel, but finally, we changed from steel to the high strength concrete because as far as we use steel, maintenance cost is have to take into count. So finally we use a concrete structure, but the compression side is okay, but the tension side we use some processing tendons. Fortunately, I have an experience of corrugated steel web and the composite truss, and each structure has advantage and disadvantage. The corrugated steel web, the connection detail is very, very simple because of the connection is located along the longitudinal direction. But composite truss, every force is concentrated on the nose. So the detail is very, very complicated and cost a lot. So the first step, we confirm the panel test. At this moment, they are steel butterfly, but finally we use high strength concrete, and we confirm the beam behavior, especially the connection here and here. But we confirm that we can use the present specification in the shear strength at this area. In detail design, we offer the highway company to use butterfly web, and we submit many, many documents in the 10 years R&D. So finally, they convinced to use these new technologies because it's very, very advantage because the structure is 15% lighter than the conventional box girder. This is a photo during construction, and the panel was prefabricated in our concrete factories, and you can see the thickness of the panel is only 15 centimeter, no reverse, reinforced by the processing tendons. So finally, we got an award, FIB Outstanding Structure, 2018. Okay, so the inside of view. So the highway company, the maintenance people surprised because inside the box girder is very, very bright. They don't have to carry a flashlight when they check the concrete. So everybody happy. Finally, the structural sustainability. I'm a convener of the TG 1.5 structural sustainability since 2013. We take a long time because every time the discussion through the model code 2020 and also especially after the COVID-19, every direction go to the carbon neutrality. So we have to rethink the definition of structural sustainability but we have to launch some document a couple of years later. So firstly, maybe the most of the bridge engineers agree with we have to focus on the beauty of the bridge. This is a beauty in architecture, everybody knows. And also you can say the same things, beauty in structure, useful, sturdy, and beautiful. We call this is a structural elegance. For example, functionality, this is a bridge in London. During the boat passing under the bridge located 90 degrees. So it's very, very clever solution. I think this is the functionality and the structural efficiency. As I said before, that this is a very clever solution. And beauty of form, but at the same time, the designer can explain each form's meaning of each form structurally. So these three elements need to realize structural elegance, I think. So again, I'll show you. This is very, very interesting photos. Jean-Francois gave me these photos. So after the third Bosphorus bridge construction, he passed away. He's a good friend and he's a very good bridge engineer. But in 2004 FIB Symposium, he showed these photos. I was shocked because Bessie Bridge by Maillart, 1933, the document is very, very small. Of course, it's a calculation by hand. But in 20,000, the Bessie Bridge strengthened by the present code, which has the many, many documents you can imagine. After this, I confirm this tendency in my company. So I was entered the company 1980. At that time, the three-span, very, very popular box girder bridge. The document page is only the 300, 400 by hand, of course. But the document page is increasing rapidly. Now it's like 2,000, 3,000, 4,000, mainly the output of the computer. So I don't like to see the detail. And at the same time, specification page is increasing. So I ask you, the potential engineers are increasing at the same time? Please think about that. This is the slides by Aurelio. This is very interesting. The Maillart, over that time, the page of the specification was only 12. But soon, the specification increasing double, 24 pages. So at that time, Maillart complained because of they didn't need the thick specification, but only 24 pages. So I can imagine the Eurocode too, how the Maillart would say to see this volume of the specification. So this is our problem or not? So how our technologies really progressed? Are we still creative? So this is Jack Green, professor of the University of Texas, and Olivier's the supervisor. And he said in the 1999 symposium, small minds and small rules stifle creativity. I fully agree with his words. So keys of inspiration. This is a point of view of the brain science. I watched the TV and the brain scientists explain these words. During mind wandering is the technical word. Default mode in the brain network is working a lot. So the default mode means the zone out. So nothing to think. But at that time, the brain worked very well. But he said 60 to 70% of brain energy is used in this default mode. So zone out is very important for us to inspire. And in my case, walking, I don't run, but walking time and also taking a bath and the business trip to the Tokyo to Osaka something. So I thought nothing, but at the same time, I inspired something, but in order to do that, we need a lot of input into the brain. If it is not meaningless for you, so input in the brain and also the zone out time, so something is connected. So please get input, many information, and to keep the time of the zone out. Okay, finally, I have to talk about the sustainability. So this is data from ETH and the EPFL. This is very important for us. So the cement, 60% cement is used for the structure concrete for us. So this is the 1.68 billion tons CO2 emission, about 5% of the whole of the world, huge amount. So we have the responsibility to reduce this. Everybody explained before my presentation. And what's the key? One is lightweight structure with high strength concrete nowadays. But at the same time, high strength concrete use a lot of cement, hopefully with low carbon technologies. And third, high durable structure, it is very important for no maintenance or minimum maintenance. And finally, remanufacturing. So not reuse, not recycle, remanufacturing with monitoring and assessment technologies for the circular economy. I give you the one clue. We have R&D and zero cement concrete and with aramid fiber concrete. So this is the cover photo, then the latest new issue of the structure concrete. Please see only the photo, no paper inside, unfortunately. But we are writing a paper for the next Congress. But is it equal to the Pantheon? Nobody knows, because the plastic fiber is a very new material compared with the concrete. I try to calculate the difference by using Attisholz girder, 37-meter length, conventional girder, and zero cement concrete and AFRP. But this time, the strength of the concrete is more than 150 MPa, but I didn't change the dimension of each members. So this is the result. A1 to A5, the conventional concrete girder, the CO2 emission is 1.3 ton CO2 per cubic meter. And at the same time, zero cement concrete and aramid fiber is 0.4, which means 70% reduction. But after the construction, during the service, the CO2 emission is much bigger. So maybe the Swiss is the same, and in the highway in Japan, we use a lot of de-icing salt during winter. So this salt attacks a lot. Now we rebuilt the reinforced concrete deck. They are 50 years old because heavily deteriorated, changed to the precast process concrete. And highway companies, engineers sometimes says the maintenance costs sometimes the same as the construction and also double. So I put this words, and B1 to B5 is almost the same, 1.3 to the double, 2.6. On the other hand, zero cement concrete, and aramid fiber is zero because no maintenance. So totally conventional concrete 2.6 to 3.9 ton, and also zero cement concrete is still 0.4, which means the 85% to 90% reduction of the whole life of the structure is very huge amount. And I have to talking about the cost. So it depends on the carbon price. I assume the 150 euro per ton, which means the 330 euro to 525 euro per cubic meter. I think if this bar is precise, this is applicable, acceptable price of the increasing of the new technologies. So we have to convince the owner, if you need low carbon technologies, you should pay. Because by the 2050, we have to reduce huge amount of CO2, which means the CO2 depends on the carbon price. Very, very huge money. And also remanufacturing, different from the reuse, because after the demolition, the members come back to the factories to confirm the strengths, its assessment technologies, and also during service, we need monitoring technologies, but we need the development, research and development in this area. So after back to the factories, every member is reborn, the new one. So the recycle, we call this the marriage cycle, and the firstly, we can reduce completely the CO2 because it's already done. So this kind of technology is very, very necessary for the next generation. Okay, let me conclude my presentation. Nature of sound conceptual design never change. And innovative conceptual design from R&D has been done for a long time. The example, the Toroha. Conceptual design is the most creative stage in design process. Maybe you can agree. Design tools, new materials and structures are key which lead to the innovative conceptual design. However, only a pen and a sheet of paper are enough for sound conceptual design. A new factor, climate change reaction, should be taken into account from now on. 2050 is your era for the young generation. I don't think I'm survived at that time, but as the experienced engineers, we have to show, okay, this way, maybe, this way, maybe, but the action is done by the new generation. Be creative. Thank you very much.
Thank you very much, Akio. Very interesting, very important presentation. Thank you very much.